Good morning all. Today onwards we are going to start online classes. So for chemistry I plan to start with volume 1. Volume 1 totally contains 7 lessons. First 5 lessons under inorganic chemistry and the next 2 lessons under the physical chemistry. So now I am going to start with unit 1 metallurgy. So this lesson is under inorganic chemistry. So this is the extract of the lesson mind map. So in this lesson we are going to learn about metals, so on its application of the metal, so and also how we are going to extract the metals from the ores. So 3 main processes are there. First one is concentration of the ore, second process is the extraction of the crude metal, and the third process is the refining process. So next I am going to start with a small introduction. So first one is metallurgy. So metallurgy means the science of study about metals and its uses. So and that extraction of the metals from the ore, that also comes under metallurgy. So we are getting that metals from the top layer of the earth surface in native form or in the combined form. Native form means here pure form. Some metals like gold, silver, platinum, copper. So these metals are, we are calling it as the least reactivity metals because these metals are not easily react with the other metals. Some metals we are getting only in the form of combined state as oxide, sulfides and the silicates. So oxides means here metal reacts with the oxygen, we are getting the metal oxide. Metal reacts with the sulfur, we are getting the metal sulfide. Metal react with the silica material to form the metal silicates. So we are telling that alkali metal as the more reactivity metals because this alkali metal is easily react with the other metals. So next, in ancient peoples use some metals for their usage. They used copper coins, iron swords and the lead pipes. So they knew how to extract that metals from the ores. But in modern world, we are using more different metals. We also combine one metal with the other. So the mixture of one metal with the other only we are call it as alloy. So example for alloys is bronze, brass and the duralumin. Brass is the mixture of 70% copper and 30% zinc. So we are using this brass for the for making electrical equipments. So next one is bronze. Bronze is the mixture of 80% copper and 20% tin. So we are using this bronze for making statues, bells, etc. So next one is duralumin. Duralumin is the mixture of 96% aluminium and 4% copper. We are using this duralumin for making aircraft manufacturing. So next one is mineral and ore. So mineral is the what are the substance we are taken out from that nature by mining is called mineral. So we are getting this mineral in native form or in that combined form. So already I gave examples for native form and combined form in the previous slide. So next one is mineral. So mineral means, so in minerals we are getting in mineral the metal may be present in a fewer amount or in that more amount. So that a percentage of metal may be vary. So next one is ore. So in mineral, the percentage of metal is in higher percentages. You call it as ore. So for example, in iron, iron is present in more than 800 minerals, but hematite and magnetite is, we call it as the ore of iron because this hematite and magnetite only having more amount of that iron. So next example, aluminium. So aluminium is present in both bauxite and the China clay. In the bauxite, 70% of aluminium is there, but in China clay only 10 to 13% aluminium is there. So ore of aluminium is bauxite. not the China clay. So next one is the extraction of the metal. So extraction means the separating of the metals from the ore. Only we are calling it as extraction of the metals. The three main processes are there. First one is concentration of ore. Second one is extraction of crude metal. Third one is the refining of crude metal. So the first process, concentration of the ore. Four methods are there: gravity separation or hydraulic wash. The second method is froth flotation. The third method is leaching, and the fourth method is magnetic separation. So first one is concentration of ore. Concentration of the ore. In the concentration of ore, we are removing the impurities from the ore. Actually, this is the first step in the metallurgy. So next one is gong. Gong means along with that ore particles, some other impurities are present. Impurities means here non-magnetic impurity, rocky materials and the siliceous matter. So this combination only we are calling it as the gong. So there are four methods are there, four methods are there in the concentration of the ore. First method is the gravity separation. So this method is fully based on the gravity separation. So first we need to take that powdered ore. Next we need to show that powdered ore in the running water. The lightweight gong particles are moving along with the running water. The heavier gong particles are settled down. So like that we are separating that impurity from the ore. So this method is applicable for native ore like native ore like gold, silver, and oxide ore like hematite and tinstone. Next method is the froth flotation. Froth means here some air bubbles. Some air bubbles is floating in that upper layer of the water. So that only we are calling it as the froth flotation. So in this method, first we are going to take water, froth agent. Here froth agent means eucalyptus oil or the pine oil and the collector. Here we are using the sodium ethyl santate as the collector. So everything is mixed and we are taken in that tank. So afterwards we are pouring that ore through the feed. That stirrer is rotating here. The impurities is always wetted with water only, and that ore particles is always wetted with oil. So the oil oil never mixed with that water, so it behaves like the hydrophobic. So the layer of oil is seen here. The ore particle mixed with the oil, it forms this separate layer at the top that only we are collected in the tank. So this method is applicable for sulfide ores like galena and that zinc blende. Sometimes both galena and the zinc blende are mixed with each other. So from that we need only galena. So we need to mix with sodium cyanide or the sodium carbonate. Here zinc sulfide is act as the impurity. So the zinc sulfide react with the sodium cyanide, forms the sodium cyanide complex here. It forms the complex and settle down. So we have collected that lead sulfide ore from the froth. Next method is leaching. So in this method, ore first we are going to dissolve in that switchable solvent. So and metal settle down as the complex here. So in this method, four methods are there: acid leaching, cyanide leaching, ammonia leaching, and the alkali leaching. So the first method is cyanide leaching. So using the cyanide leaching only, We are going to separate that gold ore from the gong particles. Here gong means impurity. So the impurity for gold is aluminosilicate. First we need to take that ore in that powdered form. Next we need to mix that powdered ore with that sodium cyanide. So we are getting the gold cyanide complexes. So the gong particle impurity is not soluble in that sodium cyanide. So it is in the insoluble form. So this is the equation. The crushed gold ore react with the sodium cyanide, use the gold cyanide complexes. From that we need only the pure gold. So in the next step, we are mixing that complex with the zinc. So this step only we are calling it as the recovery of metal from complex by reduction. So already you know what is oxidation and what is reduction. So oxidation means loss of electron, reduction means gain of electron. Here cyanide gains the electron from the zinc. The cyanide takes the electrons from the zinc. So it leaves that gold. So the zinc and the cyanide forms the zinc cyanide complex. We are getting the gold in the zero oxidation state. So next method is ammonia leaching. So this method is applicable for nickel, copper and the cobalt ore. So in this method we are mixing that ore with that aqueous ammonia. So both are reacting with each other. Then finally we are getting the soluble complexes. Nickel react with ammonia. We are getting the nickel ammonia complex. Copper react with ammonia. We are getting the copper ammonia complex. Then cobalt react with the ammonia. We are getting the cobalt ammonia complex. The gong particles, the impurity are not soluble in the ammonia. So it is insoluble. So it is an insoluble state. So the gong particles which are present along with the ore is iron oxide or iron hydroxide, and sometimes aluminosilicates also present as impurity. Next method is alkali leaching. So in this method, the powdered ore we are mixing with alkali. So alkali, we are either taking sodium hydroxide or the sodium carbonate. So both are reacting with each other. Finally, we are getting the soluble complexes. So this method is applicable for aluminum ore. So bauxite we are taking here. Bauxite is actually the ore of aluminum. Bauxite is reacted with alkali, forming the soluble sodium aluminate. So from that we need only the aluminum. So in the next step we are passing that carbon dioxide gas. Finally we are getting that aluminum as precipitate. Precipitate means aluminum is settled down. The impurity which are present in that ore is iron oxide and titanium oxide. So this is the equation. Al2O3 is that bauxite ore. So we are reacting this ore with that alkali NaOH. So we are getting the soluble sodium aluminate. So from that step, we need only aluminum. So we are passing CO2 gas to the complex. So we are getting Al2O3.XH2O. Here X is the number of water molecules. So from that we need only aluminum. So on the next step we need to heat that oxide. From that water molecule escapes out in the form of vapor. So we have collected only the pure aluminum. Next method is acid leaching. So this method is applicable for sulfide ore like ZNS and PBS. ZNS is zinc blende. ZNS is zinc blende and PBS is galena. Here first we are going to take that insoluble sulfide. So insoluble sulfide we are going to mix with that hard sulfuric acid. So both are reacting with each other. Afterwards we are getting that ore in the form of sulfate. Here sulfide is converted into the sulfate. See the example. Here zinc sulfide we are taken in the form of a solid. So we are going to mix that zinc sulfide with the hot sulfuric acid. So after the addition of sulfuric acid, here sulfide is changed into the form of sulfate. So we are getting that sulfate in that aqueous form, that is in the liquid form. So we are getting that sulfur in the elemental sulfur in the solid state. Next method is the magnetic separation. So this method is based on the magnetic properties. So from this method, we are going to separate the magnetic material from the non-magnetic materials. So magnetic materials means the material which are attracted by the magnet. So the magnet is nickel, cobalt, iron, nickel, cobalt. So that is the magnetic material that alone attracted by the magnet. So first we are going to pour through the funnel. So and then ore is moved through that moving belt. So inside the moving belt two roller is there. So one roller is made of magnet, another is the normal one. So the ore is reaching, the magnetic particle is attracted by the magnet which are present in that magnetic wheel. So afterwards we are collecting that magnetic material in the magnetic ore tank. So on the non-magnetic particles we are collected in that another tank. So like from this method we are separating that magnetic material from the non-magnetic materials. So using this method we are separating the tin stone from the wolframite. So and then pyrolusite chromite containing the magnetic property. So we are separating this pyrolusite and the chromite from the siliceous material. So here siliceous material is the sand particles. So the second process is the extraction of the crude metal. So extraction means we are separating. Crude metal means still some impurities which are present in that metal. So two steps are there. The first step is the conversion of the ore into the oxide. The second step is the reduction of the metal oxide to the metals. See the first step now, conversion of the ores into the oxides. Two methods are there. First one is roasting and the second one is the calcination. So in the roasting, we are heating that ore in the presence of excess of oxygen. But in calcination, we are not using that oxygen. See here, the sulfide ores is converted into the oxide form. So in this method, we are heating that. In this method, we are heating that ore with the excess of oxygen. Here, sulfide ores is converted into that oxide form. So why we are converting that sulfide into oxide form means, so it is not easy to remove that metal from the oxide form. From the sulfide form. So that only we are converting that into oxide form. So from the oxide form, it is easy to remove that metal using the reduction method. So the first example is lead sulfide. Lead sulfide, we are reacting with the heating with the oxygen, use the lead oxide and the SO2, sulfur dioxide. So second example is zinc sulfide, react with the oxygen, use the zinc oxide and the sulfur dioxide. Next example is cupric sulfide, react with the oxygen, use the cupric oxide and the SO2, sulfur dioxide. Here the byproduct sulfur dioxide causes the air pollution. So you need to convert that sulfur dioxide into the sulfuric acid to reduce that air pollution. So while heating, some impurities like arsenic, sulfur and the phosphorus is converted into that volatile oxide form. So it escapes in the form of vapor. So next one is the calcination method. So in this method, we are going to heat that ore in the absence of oxygen or with that little amount of that oxygen. Here oxygen is present in the carbonate form. So while heating, that carbonate form is decomposed into oxide form. So we are getting the metal oxide and the CO2 as the byproduct. So lead carbonate we are taking. So we are heating that lead carbonate in the absence of air. So we are getting that lead oxide and the CO2 as byproduct. So next example is calcium carbonate. So we are heating the calcium carbonate in the absence of air. So we are getting that calcium oxide and the CO2 as byproduct. Next example is zinc carbonate. Zinc carbonate while heating. So we are getting the zinc oxide and the CO2 as the byproduct. So next example, MgCO3 magnesium carbonate and the calcium carbonate. So while heating, it decomposes into magnesium oxide, calcium oxide and the CO2. See the next example here, Fe2O3 iron oxide dot 3H2O. Here H2O is present along with that ore, so that only we are calling it as the water of crystallization. So this ore look like the crystal. So while heating, the water molecules goes out in the form of vapor. So next example, while heating that aluminum oxide, the water goes out in the form of vapor. So we are getting that aluminum oxide here. So in the calcination process, CO2 is expelled out. So next method is the reduction of the metal oxide. So we need some reducing agent to reduce that metal oxide. Here the metal oxide are reduced into the metal using some reducing agent. So common reducing agents are carbon monoxide, hydrogen, aluminum and the sodium. Carbon is not used as the reducing agent for sodium, potassium and the aluminum like active metals. So carbon monoxide is used as the reducing and not used as the reducing agent for zinc oxide and the aluminum oxide. So how we are selecting that reducing agent means, so we are selecting that reducing agent reducing agent for particular metal oxide using that Ellison diagram. So I will explain about that Ellison diagram in the next upcoming video. So first method is smelting. Smelting means here concentrated ore we are mixed with a reducing agent and the flux. So flux means here one chemical substance only. Finally, we are getting the pure metal and the slag. Slag means here impurity. So we need to heat that reaction at the elevated temperature. Here iron oxide, we are reacting with that reducing agent CO. So we are getting the pure metal and CO2 as byproduct. So what we are SiO2 is a gone means SiO2 is the impurity is already present in the Fe2O3. CaO we are adding as the flux to that reaction. Both the flux and the impurity present in Fe2O3, SiO2, both are reacting with each other. We are getting the CaSiO3 as slag. Slag means here impurity. After the removal of the impurity, the Fe2O3 react with the reducing agent. So we are getting the pure metal. Next example is copper extracted from the copper pyrites. Here CuFeS2 is the copper pyrite. So we are going to heat that copper pyrite in the presence of oxygen. So we are going to heat that oxygen in that high temperature. So the solid form of copper pyrite is changed into that decomposed and changed into that liquid form. So we are getting FeS, Cu2S and the SO2. Again FeS, the product FeS again react with that oxygen. We are getting it is changed into that FeO. Here sulfide form is changed into that oxide form. So after FeO react with that flux SiO2. Here SiO2 is the acidic flux. FeO is that impurity which is present in that copper pyrite. Both the impurity and the flux react with each other. We are getting the FeSiO3 as a slag. So we are getting the slag in the solid form. Here the Cu2S, that is cuprous sulfide, it is in that solid liquid form. So this one react with that oxygen. We are getting the cuprous oxide. So we are getting that one in the solid liquid form. So after that, this cuprous oxide reacting with the cuprous sulfate, we are getting the copper in that pure state, and SO2 goes out in the gaseous state. In this copper layer, SO2 comes out in the form of vapor like bubbles, so that only we are calling it as the blistered copper here. Here we are not adding any reducing agent, so we are calling it as the self-reduction. So next method is reduction by carbon. So in this method, metal oxide, we are reacting with the carbon. So we are getting that pure metal and carbon monoxide as the byproduct. So this method is not applicable for carbide forming metals. So example for this method is zinc oxide react with the carbon gives the zinc plus carbon monoxide as byproduct. So next example, manganese oxide react with the carbon gives the manganese plus carbon monoxide as the byproduct in the gaseous form. So chromium oxide react with the carbon gives the chromium and carbon monoxide as the byproduct. Next method is reduction by hydrogen. So for what type of metal we need to use the hydrogen as the reducing agent? So less electropositive character. So electropositive character means releasing electrons. Less electropositive character metals like Fe, Pb, Cu and the Ag than the hydrogen. So hydrogen releasing electrons to oxygen than the Ag in the first example. See the first example now, silver oxide, we are reacting with the hydrogen. Here hydrogen we are taken as the reducing agent. Here hydrogen releasing more. So in the first example, hydrogen releasing more electrons to the oxygen than the silver. So hydrogen and the oxygen forming the water here. So oxygen leaves the silver in the zero oxidation state. So in the next example, iron oxide, we are reacting with hydrogen. Here hydrogen is act as the reducing agent. So hydrogen releases electrons to the oxygen. So hydrogen and the oxygen forming the water molecule. So and we are getting that silver in the zero oxidation state. So this method is somewhat different here. Nickel oxide, we are reacting with the carbon monoxide and hydrogen. So the collective CO and the H2 both collectively are called it as the water gas. So it is a highly inflammable substances. So both are reacting with each other. So we are getting the pure nickel here. CO is goes out in the form of CO2 and the H2 is expelled out in the form of water. So next one is the reduction by metal. So we are using some metals to reduce the metal. Here we are using that aluminum powder as the reducing agent. For this method, we need excess of heat for start. So we are adding magnesium and the barium peroxide here. Barium peroxide and the magnesium gives out giving a barium oxide and the magnesium oxide. So this reaction gives more amount of heat and that energy. So nearly 2400 degrees Celsius heat is liberated and 852 kilojoules of energy is released. So this method is this aluminum powder is used to reduce that chromium oxide. That aluminum metal oxide is reduced aluminum powder is used as the reducing agent here. Finally, we are getting that metal and the aluminum oxide. See the equation now. Cr2O3 chromium oxide react with the aluminum powder. We are getting that chromium metal and the aluminum oxide as the byproduct. So why we are called this method is aluminothermite process means, so aluminum is used as the reducing agent and more amount of heat is liberated during the reaction. So only we are call it as aluminothermite process. So apart from that aluminum powder, some other active metals is also we are using as the reducing agent. So the active metals like sodium, magnesium, calcium, potassium. See the first example now. Boric oxide react with the sodium, gives the boron and the sodium oxide. Rubidium oxide reacts with the magnesium, gives the rubidium and the magnesium oxide. Titanium dioxide reacts with the magnesium, gives the titanium and the magnesium oxide. Thorium dioxide reacts with the calcium in the presence of 1250 Kelvin, gives the thorium and the calcium oxide. So next one is the auto reduction. Here we are not adding any reducing agent. Simply we are roasting the crude metal. Here HGS we are taken here. HGS is Chinnabar. So we are we are heating in the presence of oxygen. Use that pure metal and the SO2 is comes as a byproduct.